Okay, so thank you.
Hang on, wait. Let me introduce you. Let me introduce you.
Sure.
So,
Sorry.
yeah, it is my great pleasure to introduce Jianming Bian, who has come all the way from UC Irvine to give a fantastically interesting talk to us about neutrino oscillations and deep learning. And thank you very much for visiting us. And I'm sure we'll all enjoy it. Please go ahead.
Okay. Thank you for invitation. I'm from your neighborhood. Today, I'm gonna talk about recent results and machine learning applications in two neutrino experiments, NOvA and DUNE. So a few words on neutrinos. Neutrinos are elementary particles with little mass and no charge. They're leptons. And the idea of neutrinos were postulated by Pauli in 1930s to save energy conservation in beta decays. And they were first observed in 1950s by Reynolds and Cohen. And neutrinos are very abundant, and there are many sources that can generate neutrinos, such as reactor, supernova, cosmic rays, and elementary elements in the Earth, and also from the sun. But today I'm going to talk about the man-made neutrino sources using accelerators to generate neutrino. The two experiments, NOvA and DUNE, are both accelerator neutrino experiments. Since neutrino only involve in a weak interaction, they're very elusive, so we need to build a gigantic detector to find the neutrinos. And here's a slides for neutrino oscillation. So we know that there are three flavors. Under standard model, there are three flavors of neutrinos. Electron neutrino, muon neutrino, and tau neutrino, and they're antiparticles. Neutrino oscillation means that neutrinos produced at a specific lepton flavor, for example, nu mu, can later be changed to a different flavor during their travel. And this observation won the Nobel Prize in 2015. And the rate of the change of the in the neutrino oscillation depends on the neutrino energy and their travel distance. So for example, you generate some neutrino here, muon neutrino, and at a distance L, after the neutrino travel from here to here, you might measure the neutrino as the electron neutrino. The flavor changes. And here is why. The neutrino oscillate because their flavor eigenstates are not their mass eigenstates. The flavor eigenstate means that the type of neutrino that you can measure, either electron neutrino, tau neutrino, or muon neutrino. And mass eigenstates are the states with a certain mass. And under standard model, the three flavor model, so you can use the PMNS matrix to convert the mass eigenstates into the flavor eigenstates. And this PMNS matrix is usually parameterized by the three mixing angles. Sit1, 3, Sit2, 3, and Sit1, 2, 3, and Sit1, 3. And then another parameter is the CP phase, del CP. And CP phase, this angle is to describe the difference between neutrino and antineutrinos. And here's the detail of this PMNS matrix, and the parameters are here. And then we include two extra parameters, the two squared mass difference among these three mass eigenstates, delta m squared 2, 1, and delta m squared 3, 2. And in total, there are six free parameters that can describe the neutrino oscillation probabilities. So remember, this is for the standard scenario, standard physics scenario with three flavors of neutrinos. And the previous experiments has made many measurements to the mixing angles and have a pretty good resolution, but there are remaining fundamental questions to be answered by neutrino oscillation experiments. So one big thing is the CP phase angle. The CP phase, as we just discussed, is used to describe the difference between neutrino and antineutrino in their oscillation. And this angle, or we call it CP violation, can give us an implication for matter and antimatter asymmetry in the universe. We know our current universe is made of purely matter instead of antimatter. But assuming that we have the same amount of matter and antimatter generated in Big Bang, why we now only have matter remaining? So the matter and antimatter must behave differently when time passes. And from the quark sector, quark compose say barons like a proton and neutrons. And from the quark sector, we know that there's some difference between a matter and antimatter. The CP is violated. But the amount of CP violation we found from the quark sector is not large enough to explain why we now have a purely pure matter universe. So the hope is that in the lepton sector, like neutrino, we found enough amount of CP violation, and then hopefully this can solve the mystery that we only have a matter universe. Another big question is the ordering of the mass eigenstates of the three neutrinos. And so from previous experiments, we can measure the absolute value of delta m squares, but we do not know the sign of this delta m square. So we do not know if the third mass eigenstate is heavier than the first and second. So m3 is greater than m12, or m12 is greater than m3. So in the first scenario, so when the m3 value is greater than m12, we call it a normal mass ordering. And for the case that m12 greater than m3, we call it inverted mass ordering. So the big question is how the neutrinos are ordered. And this ordering can help us to solve the absolute neutrino masses. And then if you put the neutrino masses into this big picture with other elementary particles, so it can help to create a grand unified theory to combine our forces. In addition, the ordering of neutrino masses will guide the next generation of so-called neutrino-less double beta decay experiments. And the purpose of this neutrino-less double beta decay experiments are to figure out whether neutrino are there the antiparticles. So, or in other words, if they are Mariana particles. And the third question is octant of C23. So we know that C23 is close to 45 degrees, but the question is whether or not it's exactly equals 45 degree, or it's greater or less than 45 degree. So the long baseline accelerator neutrino experiments, such as NOvA and DUNE, are designed to solve these questions using man-made neutrino sources. Little more detail about how we figure out this problem with neutrino beam. So you can see we have a source of neutrinos, either muon or anti-muon neutrino. And then, so right by the source, we use a so-called near detector to monitor neutrinos before they oscillate. And then after the neutrino travel a long distance, like 1,000 kilometers, we measure the neutrinos with a gigantic detector. We call it a far detector. Usually it's multi-kilotons. And we can either measure the remaining muon neutrino, like mu mu and nu mu, anti-nu mu, or we can measure the rate of muon neutrino oscillate to electron neutrino. So we call this the disappearance of muon neutrino disappearance, or the electron neutrino appearance. And you must wonder why those neutrinos do not interact with the Earth during this long distance. This is because neutrino only involved in weak interaction. So although there are many neutrino passes, but only very few of them actually interact with the Earth. So they mostly can reach the far detector region. However, because the neutrino interaction is very big, we need to build a very large detector to collect enough statistics to measure the neutrino oscillations. And more details about the source. So we first use accelerator to accelerate protons to very high energy, and then use this proton to hit a target, usually is graphite. And then the graphite generates this charged particles like pion and cation. And those charged particles are focused by a magnet, by a set of magnets called horns, and to point to the direction of the far detector. And in the decay pipe, those charged particles will decay to neutrinos, and therefore you have a neutrino beam pointing to the direction of the far detector, and then you can measure it. Now here is the picture that we taken for the accelerators at Fermilab near Chicago. So as you can see here, protons are generated here and injected into this big accelerator, and the protons are accelerated to 120 GeV and hit the target here, the black point, and then generate a neutrino beam to Minnesota. The NOvA far detector is in Minnesota, so the distance is from Chicago to Minnesota. The next generation of neutrino experiment is called DUNE. We still use the same accelerator, but this time the neutrino beam is pointed to South Dakota in DUNE's far detector site. Then how we really measure determine the probability of neutrino oscillations in this long baseline experiment. So we have two type of measurements. One is new mu disappearance. The other is new E appearance. The new mu disappearance measurement means that we measure the survival rate of mu neutrino after a long travel distance. The probability of new mu goes to new mu. And from this equation, you can see that we can measure the absolute value, because there's a sine square, absolute value of delta m square, as well as the sine square to 3 with very high precision. New E appearance means the probability of the new mu neutrino oscillate to an electron neutrino, or the anti-new mu goes to anti-electron neutrino. And this is the equation. And from this equation, you can see that we can measure the sign of the delta m square value, because so it's here. And so we know the sign, so we know the ordering of the 3 mass eigenstates. And we can also measure the CP phase, delta CP, as well as the octant of C23. Sorry about that. Okay, so now go to our experiment, NOvA. So the current long baseline neutrino experiment in the US. And we generate a mu neutrino beam at Fermilab near Chicago. And we build the near detector to monitor the neutrino before oscillation in Fermilab, also close to Chicago. And then we send the neutrino beam to Minnesota, a distance of 810 kilometers. And the far detector is in Minnesota, Ash River. And the detector is on surface. In addition to that, there is 40 milliradians angle between the neutrino beam and the far detector. This is because in this way, the energy of the neutrino is peaking around 2 GeV, which is the maximum of the oscillation. Therefore, we can improve the oscillation sensitivity and reduce the unnecessary unoscillated neutrino backgrounds. Here is our data. So the neutrino beam, so the muon neutrino looks like this. There's a peak around 2 GeV, and this is a anti-neutrino beam, so mostly anti-nu mu events. You can see the anti-nu mu is much less than nu mu because the cross section in the detector is much lower. And here's our data set. We have 13.6 10 to 20 POT. for the neutrino beam, and 12.5 times 10 to 20 POT for antineutrino data. So POT means the protons on target. This means that we generate this many protons hit the target. It's a way that we count we count our data set, and we already exceed our design goal. So the power is more than 700 kilowatts since January 2017, and we are working on improving the beamline targets, magnets, and improve the accelerator to achieve a better power. And here is a data accumulation with respect to years. The detectors, so we have far detector and near detector. The far detector is 14 kiloton, very fine grained with liquid scintillator and has many detector cells. And also have a 300-ton near detector. The near detector is functionally identical to the far detector. And as you can see here, the detectors are composed of PVC tubes, and in each tube in the far detector is about 16 meters long. And in each of this PVC tube, we fill it with liquid scintillator and then route a wavelength shifting fiber in it and attach to a photosensor. In this way, we can mirror the signal from the neutrino interactions. And the cells in the far detector and near detectors are arranged in planes, and then the planes are assembled in alternating vertical and horizontal directions. So you have X view and Y view readout, and then combine them together, you have the 3D information for neutrino interactions. Therefore, you can develop the 3D tracking algorithm and 3D particle identification algorithm to reconstruct neutrinos. Here are some pictures for the far detector and near detector. It gives you some sense about the size of the far detector and the near detector. They both very large. And here I give you a few examples of event display in NOvA far detector. So here's a X view only. So you can imagine there's another view, Y view, but I'm not going to show it. This is the new mu events. So we use the new mu charge current events to tag the signal, the new mu appears signal. So you can see a neutrino hit the target, hit the detector, and is converted into a charged muon, and with some hadrons. So we call this process a new mu charge current event. And this is our signal channel for the new mu disappearance analysis. And this one is for the electron neutrino appearance. So electron neutrino hit the detector and is converted into an electron with some hadron. And this is the signal for the new E appearance analysis. So you can notice that both of them have a lepton, but we just need to figure out the flavor of the charged particle. Either it's a muon or it's an electron to identify the signal. And the background is so-called neutral current events. So we still have a neutrino, but this time there's no charged leptons be generated. And this is our main background. And the analysis start with identification of neutrino, type of neutrinos. So we need to develop this PID, particle identification, to figure out whether neutrino interaction is new mu disappearance or new E appearance or background. We use a deep learning technology called CVN. It is a convolutional neural network, and the technology is based on modern image recognition developed in computer science field. And this neural network can extract the feature directly from raw pixel maps. That means you don't need to intermediate steps to reconstruct the particle identification, and then you can directly put this pixel map input to the neural net, and then it tells you the type of interaction like this. So it will generate a score from 0 to 1, and here we use the new appearance signal as an example. You can see the signal is peaking around 1 and background is peaking around 0. And if you simply add a cut here, you can see it select a lot of signal with very few backgrounds. And the statistical power from this convolutional neural net is turned out to be 30% more than the traditional likelihood-based particle identification, PID. Then after the PID, we do energy reconstruction and extrapolation. So we basically add up the hadronic energy. So this is the interaction of muon neutrino, the charge current event. So we add up the muon energy, like this blue box, and the hadronic energy, this red box. Add them up with some correction factors, we get the total neutrino energy for nu mu disappearance signal. Please notice that this is a traditional method and with not that good resolution. We'll talk about the new method using deep learning that we are developing for NOVA later. And after we have neutrino energies, we can do this extrapolation. The extrapolation means that we first measure the neutrino data in the near detector before oscillation. We compare the data in Monte Carlo simulation difference in the near detector, and we found the difference. And the difference is used to extrapolate it to the far detector and correct the far detector Monte Carlo simulation prediction. Therefore, we have the data-driven method to significantly reduce the systematic uncertainties. And also the systematic errors determined in the near detector are also extrapolated to the far detector. And then we have the far detector neutrino energy spectrum prediction. Here I show you the systematic errors extrapolated from the near detector to the far detector by categories. And then we have the far detector prediction, and then we look into the far detector data, or we call open the box to see the real data. So in addition to the convolutional neural net selection, we have an additional boost decision tree to reduce the cosmic ray backgrounds. This is a more traditional machine learning method rather than the deep learning. And the left plot, I shows you the nu mu disappearance like data and Monte Carlo. So you can see we found 211 events in the far detector from the nu mu. And for the anti-nu mu candidates, we found 105 events. The dots are the real data in the far detector, and the histograms are the Monte Carlo prediction after the correction from the near detector and after reweighted by the oscillation parameters. You can see that they match pretty well. And then we select the electron and anti-electron example from the electron beam and anti-electron beam. In addition to the energy spectrum, we also create another beam here, which is close to the top of the detector. In that region, we use tighter cosmic ray rejection cuts and to improve the significance. And for the energy spectrum, we extrapolate the spectrums in two PID bits, one low PID, one higher PID bit. In this way, we can improve the significance of the NUE and anti-NUE measurements. And from the neutrino beam, we found 82 electron-like events. And from the anti-neutrino beam, we found 33 anti-electron-like events. And backgrounds are properly estimated using the corrected far detector, Monte Carlo. And we found that we have more than 4 sigma significance for the anti-electron neutrino appearance. And after we have this nu mu, anti-nu mu, NUE, and anti-NUE data, in the far detector, we can extract oscillation parameters by fitting the oscillation weighted far detector Monte Carlo to the far detector data. This is what we are doing. So we use a frequentist analysis called field cousin approach to infer oscillation parameters. And we constrain one of the mixing angle, psi squared C213 to the average value from the reactor data measurements. And then we perform the fit, we get the best fit and contours. So I'll go through them one by one. This one, I show you under the normal mass hierarchy hypothesis, I draw the delta m square versus sine square C23. You can see these curves are the contours, and the best fit is here. So the best fit prefer the normal mass hierarchy case, and we have a pretty good measurement to sine square C23 and also delta m square. And we also, from this contour, we also find that it's the data is not disfavors the value sine C23 value 45 degree at 1.1 sigma. So it's not maximal mixed, and also disfavor the lower octant of C23 at 1.2 sigma. So our result prefer a normal mass hierarchy and the upper octant means that C23 greater than 45 degree. Now we draw these contours in a different parameter space. So we draw sine theta 23, sine square C23 versus the CP violation value. And the left plot shows you the normal mass hierarchy hypothesis, and the right one shows you the inverted mass hierarchy case. And you can find that the best fit is around C23 del CP close to 82 pi. And though we do not have a very large significance now for the mass hierarchy, it's just we prefer normal mass hierarchy with about 1 sigma, but we do exclude some regions in these contours. For example, we exclude this region, the CP equal to half pi, in the inverted mass hierarchy case with greater than 3 sigma, and we also disfavor this region in the normal mass hierarchy. So when del CP close to 3 half pi around here, so we exclude this region with 2 sigma. And yeah, so and then we compare our results with other experiments. So you can see we have consistent but better measurements to delta m square and sine square C23 compared to other neutrino experiments. And then if you look into the CP violation, CP phase, you'll find there's a tension between our measurement and the other main long baseline experiment in Japan called T2K. So they measure the CP violation in the normal mass hierarchy hypothesis at this point, and we measure it at this point, and the tension is 1 or 2 sigma. So NOvA and the T2K collaborations are now working together to develop a combined analysis with a joint fit to include all the systematics. Hopefully, can solve the mystery here in the CP violation. Looking forward for the future of NOvA, NOvA will run at least through 2025, and we have test beam programs going on, and we have potential accelerator improvement, and we can improve our ultimate scientific reach. And if we are lucky in this green shade, so the CP violation is 3 half pi, and we can measure by 2025. We can measure the mass hierarchy with a significance of 2 or 5 sigma. And if we're in this region, so the 30 to 5%, 50% of CP phase angle region, we are able to measure the mass ordering greater or equal than 3 sigma by 2025. And if we are here, it's very unlucky. Okay, so now change topic to next generation of neutrino experiment, DUNE in the US. The DUNE will use the new neutrino beam at Fermilab, increase the power of the accelerator, and also increase the baseline of the experiment. So now it will pump from Fermilab in Chicago to Sanford in South Dakota. And the baseline will become 1,300 kilometers. And the detectors will be even larger. The far detector for DUNE will be 7 kiloton liquid argon TPC detectors underground, 1.5 kilometers from the surface. And this will greatly reduce the backgrounds from the cosmic rays. And also we have a multi-technology near detector around Fermilab to monitor the neutrinos before they oscillate. And the main physics goal for neutrino for DUNE is a new appearance and new disappearance measurements, and the DUNE will make a decisive measurement to the mass ordering and CP violation. And since DUNE has large detectors and the detectors are deeply underground and also have very high intensity beam, we can also use the far detector and near detector to study supernova burst and other atmospheric neutrinos, as well as nucleon decay and other, say, beyond standard model physics. And the excavation has started in 2017, and now we are and we'll take data hopefully in late 2020s. This is for June. And here is a cartoon to show you where the far detector modules are. So this is a so-called Sanford underground facility in South Dakota. This is the very location where Ray Davis found the first solar neutrinos. But we'll build new experimental house here, huge cabins to contain these four large detector modules. And this is groundbreaking in 2017. And the depth from the surface to the experiment hall, the far detector hall, is about 1.5 kilometers. And the technology we use for DUNE far detector is so-called liquid argon time projection chamber. And it has very high resolutions because, as you can see here, so we use a huge detector to contain a lot of liquid argon. And then the charged particles generated by the neutrino interaction will ionize the argon atoms and then create this ionized electrons. And those electrons under very high voltage between cathode plane and anode wires, those electrons will drift and then provide the two-dimensional information in X and Y view. And then in the Z view, the drift time will be used to reconstruct the location in the Z direction. And because the ionizing electrons drift a very long distance, because the detector is huge, the impurity atom could attract the electrons. Therefore, the purity of liquid argon is very important to make this experiment successful. And here are some examples of the pixel map we read out from DUNE. From another liquid argon TPC experiment called microboom. We can see we have very high resolution. The pixel size is only 5 millimeter by 5 millimeters. And the NOvA, the typical pixel size for NOvA is 5 centimeter by 5 centimeter. So it's a dimension, the resolution improved about 10 times in each of the X and Y directions. And for the far detectors, we'll deploy 4 detector modules. Each one is 17 kilotons deep underground, but we'll deploy these 4 detectors step by step. The 2 far detector designs are developed. One is a single phase liquid argon detector, and the other is so-called dual phase. So it includes both liquid argon and argon gas. And for the single phase, all the wire planes, the anodes, will be immersed in the liquid argon. For the dual phase, the ionized electrons will be extracted to the gas phase and amplified in the argon gas. And the first module among these 4 modules will be a single phase liquid argon TPC. The size is 18 meter by 19 meter by 66 meters. And the drift distance between the anode to cathode is about 4 meters, and pitch size is 5 millimeters. So high resolution and huge detectors. We also have near detector at Fermilab. So we already have say conceptual designs under preparation, and basically it will has 3 components. One is the liquid argon component, and the other is a gas argon tracker with high pressure. And the third one is a tracker surrounded by a calorimeter. And combine them, these three detectors will have very good performance to figure out the the neutrino components before they oscillate. And the first 2 components, the gas argon and liquid argon components, are movable. You can see vertical to the beam direction. In this way, we can deconvolute the flux of neutrino and reduce significantly this major uncertainty in our analysis. And the idea is called DUNE prism. And here is the expected number of signal events. For the new appearance, we expect around 1,000 events. And for the new mu disappearance, it's 10,000. So it's basically an order of magnitude greater than NOVA's data. And therefore, it can decisively measure the CP violation and mass ordering using this data. And here are physics reach for the oscillation analysis. The left plot shows you the CP violation sensitivity as a function of the CP phase angle. So you can see in a large region, we can reach 5 sigma for CP violation measurement. And for the mass ordering measurement, you can see we can easily beat the 5 sigma threshold. So very shortly. And here is sensitivity as a function of year for CP violation and the mass ordering measurement. So you can see if we are lucky, within 3 years, DUNE can determine CP violation at 3 sigma. And for mass hierarchy, even at the worst scenario in 2 years, the DUNE can determine mass ordering with 5 sigma, which now NOVA and T2K are struggle for. And the technical design report for DUNE has been released here. And since DUNE has very large far detector deeply underground, and has very good separation for cation and pion, charged particles, the far detector can be used to do other beyond standard model physics, like neutron antineutron oscillation. So because you can reconstruct clearly the tracks from neutrons, and also looking for prolonged decay. Again, the good reconstruction of cation, muon, etc. And also it can be used to study high energy dark matter, the boosted dark matter. So I steal this plot from one of our colleagues from UCR, Professor Cui. And in the near detector, because we have high beam power and very highly capable detectors, we also be able to study beyond standard model neutrino. And you can see here is an example for the low mass dark matter could be measured by the DUNE near detector. And in addition, again, because of the huge detectors for the far side of the DUNE experiment, we can use DUNE to measure supernova burst as well as the solar neutrinos. Importantly, because DUNE is very sensitive to electron neutrino, the DUNE far detector is sensitive to the neutralization process in a core collapse supernova because it's dominated by electron neutrinos. And you can see here, this peak is neutralization in a supernova burst, and it's very different when you have say normal mass hierarchy and inverted mass hierarchy. So by marrying this peak, you can figure out the mass ordering using the supernova burst measured by doing experiment. And also because it's deeply underground and large detector, you can accumulate a lot of statistics for supernova burst in a short period of time. And we already built prototypes for the DUNE fire detectors. One is called the single phase proto-DUNE, the other is called dual phase proto-DUNE. They both constructed at CERN, and they both around has a mass around 1 kiloton liquid agar. And at CERN, we also generate test beam, including electron, cation, muon, proton, and pi. Using these particles with known energy and known identity, we can study the reconstruction performance, the energy resolution, and the particle identifications at CERN. And here are some pictures taken from CERN. This one is our proto-DUNE single phase, and this is the proto-DUNE dual phase. And those two pictures are inside. And for the single phase proto-DUNE, the phase one operation has done recently, and we are preparing the second run for taking new beam data. And for the dual phase, proto-DUNE is still operated, and the operation started just last year. Here are some results. We already have our first results from proto-DUNE single phase. First, you can see these very beautiful pictures in the single phase proto-DUNE detector. High resolution and very clean for 3 GeV pion, 2 GeV electron, for example, and 1 GeV pion, and this is higher energy pion. This clean picture means that the resolution and data quality is excellent. Also means that we already successfully control the electronic noise in the prototype prototype DUNE detectors. Here are some other results. So the cosmic ray DEDX is consistent with expectation, and we use it to calibrate the detector. And after the calibration, you can see the DEDX for the beam test beam protons are consistent in data and Moncara. And we use purity monitor to measure the drift electron lifetime to determine the purity, and we found the electron lifetime is greater than 20 milliseconds in the proto-DUNE single phase, which means that we already achieved a very high purity, which is required by the DUNE fire detector. Okay, now change again to the machine learning applications in NOVA and DUNE. So if we revisit the oscillation analysis in NOVA or DUNE, you can find we have these steps. The first step is particle identification, and then reconstruct energy and other kinematic variables. And then after extrapolation, we can infer the oscillation parameters by fitting the oscillation weighted fire detect Monte Carlo data. And I highlight these blue parts, the identification, reconstruction, and the parameter inference. These processes can be enhanced by applying machine learning technologies. And the core of the deep learning or machine learning reconstruction and identification is the so-called convolutional neural net that I mentioned in the NOVA part. And this convolutional neural network, or called CNN, has shown very good performance in classification problems, such as neutrino event identification and particle identification, as well as image segmentation. Means that we want to separate the neutrino, the proton, electron, or muon particles in the detector pixel map. And we are now also developing regression CNN to reconstruct the continuous variables in both NOvA and DUNE. So for example, we want to reconstruct the energy, direction, momentum, position of the interaction. And those variables will be used for the oscillation analysis, near detector cross-section measurements, and also used in the extrapolation processes. Here is one of the classification CVN developed at DUNE, so called DUNE CVN. And you can see it can perfectly identify new mu events, new events, as well as main background neutral current events. So the peak is here, shows the signal for the new E, and this one is for the anti-new E appearance signal. And the performance of this deep learning method actually already beat our best guess in the conceptual design report for DUNE, which is very exciting. We are better than our best guess before we really apply this deep learning method. Another other classification is I'll use NOvA as examples. The NOvA is more advanced developed because NOvA is the first experiment that introduced this convolutional neural net in high energy physics experiments, and we now already developed the event identifier like this. Paper is published, and also developed the identifier to identify final state particles like proton, pion, photon, muon, and electrons with very high efficiency and purity. And we also use this classification CN to do the image segmentation. Therefore, you can separate and identify, say, the final state particles like electron. These heats are caused by electron according to the CN, and these events, those heats are caused by a photon in neutrino interaction, etc. And this is for another photon. And this slide shows you the classification. Now we move on to the regression CNN. So regression CNN is still use the convolutional neural net, but this time we want to output continuous variables like electron and neutrino energy, or the interaction point, we call it vortex, or the final state particle energy, like proton electron energies in a neutrino interaction. We modify the loss function in this neural network to better represent the energy resolution, and by optimizing it in the training, we can get the neural network ready. And the left architecture is NOvA, and right architecture is for DUNE. The NOvA, we have two views, so we have these pictures as inputs, and for DUNE, we have three views, three wire planes. So we have U, V, and Z. And we combine them together as the inputs, and the output is the electron energy, neutrino energy, or the particle positions. We also weight the event with energy to reduce the energy dependent bias in the training, to make this neural net less affected by the training model. And here are some results. This is a regression CNN from NOvA. So we use it to reconstruct this electron neutrino energy. You can see resolution is much better than the traditional method based on the kinematic information. And also we found this neural net is less affected by energy, and also it has a smaller systematic uncertainties compared to the traditional method. As you can see, the error bar from the deep learning method is smaller than the traditional method, as well as the calorimetry energy method. So other examples here are the regression CNN for particle energy and neutrino energy reconstruction at DUNE. So we successfully use this CN to reconstruct the new E appearance signal energy, a new mu disappearance energy, and the individual final state particle energies like muon energy, electron energy. We found they all have better performance than traditional method, and also interestingly, we found the performance is better for a so-called uncontained muon neutrino events. Uncontained neutrino means that the part of the muon track, part of the energy of the muon exists the detector, which means that we don't have the full information of the muon, but we can relate using the convolutional neural net automatically the scattering angle to the existing energy. So in the traditional method, you explicitly write down the equation, so the multiple scattering equation to correlate the scattering angle to existing energy. But here, it's all done automatically and with a better performance than traditional method. Another regression CNN is a 3D CNN for the particle direction reconstruction, because if we want to know the momentum of a particle, we have to know both energy and the direction. So we found that because direction information is a special related variable, we found that a 3D pixel map can give us a better training in the deep neural nets. So we developed this 3D CNN based on the 3D pixel map, and you can see that the angular resolution is much better using this CNN compared to the traditional methods. So here, there are other methods for deep learning applications in NOvA and DUNE. So I just mentioned here. So we have a sparse neural nets and have a graph neural nets to develop. And these two methods can speed up training for sparse pixel map, because neutrino interaction, you can see you have huge detector, but only have a small spot of interaction in that detector. So there are many zero inputs. So these two architectures of neural nets can help to improve. Okay, one is use the sparse matrix, the other is use the graph to get rid of the issue from the zero inputs. Therefore, significantly enhance the speed of the training for the deep learning algorithm. And the third method under developing is so-called RNN, recurrent neural net. And this is ideal to combine a variable number of inputs. Therefore, it's very useful to combine the kinematic and PID information for each particle final states in a deep learning architecture, because you don't know how many final particles gonna be generated in neutrino interactions. And also, it's very useful to develop this step-by-step deep learning. So it's not a black box anymore. In each step, we can validate and study the performance and explain the performance of the deep neural nets. And so the robustness of AI and machine learning is also a concern. So we train the neutrino the neural nets with Monte Carlo, but we need this Monte Carlo training consistent with the real data. So we do two things. One is we test the robustness of the neural nets against interaction modes, energy, and systematic error, etc. And here is the example. We found that so far the regression CNN we developed have a very good robustness. And in addition, to make sure that our neural net works in data, we developed data-driven method with control examples in near detector, in far detector, and also use neutrino, also use the particle test beam. So for NOvA and DUNE. So for NOvA, you can see we select the Bremner-Strahlung shower from cosmic muon. We remove the muon from new mu events and then replace it with the simulated electron. We call MRE example. Use this data to study the performance of deep learning PID. And also we stack the pi0 example in near detector to study the robustness of the PID to identify final state particles. And these two pictures are for the beam test beam in NOvA and test beam for DUNE. And another topic, so in addition to the reconstruction, we can use machine learning to enhance oscillation parameter in inference. So traditionally, we use a frequentist method called the Feldman-Cartan approach to extract the neutrino parameters in most of the current neutrino oscillation measurements. However, this Feldman-Cartan method is very time-consuming because it searches a grid of parameter space point by point and generate many toy simulated events for each point, and then integrate and obtain the p-value for each point in that space in that parameter space. You can imagine that it's every simulation you need to consider the uncertainty, systematic uncertainty, statistical uncertainty. So it's very time consuming. So we introduced a so-called Gaussian process method. And the Gaussian process is a special case of Bayesian learning. And this method can use existing data points to predict the value of unseen points in the parameter space like this. So you just generate a small portion of this simulated data, and then you use this Gaussian process, this Bayesian learning, to to approximate the curve of the p-value of the p-value over the space of the parameter space. In this case, CP phase angle, and then you also can estimate the uncertainty for each point without really generating these toy simulations. In this way, we can significantly reduce the time and the computational cost in this Feldman-Cartan process. Here's the result we published this result in PRD. So as you can see, using this method, you can have very close estimate to the counter. So this counter is for the sine square 2C23 versus delta CP phase angle. So you can achieve 99% accuracy with this Gaussian process method, but you only take like 1%, 10% of time consumption or the computational burden to achieve this very close counter. And this method has been implemented in NOVA software, and we're working with Fermilab to develop a parallelization algorithm to really fit NOVA parameters using DOE's high performance computers. So now give a summary. So we have a good result from NOVA, precise results on sine square C23 and delta m square, and we exclude some regions for CP violation and mass ordering. And we expect we can have 3 sigma mass ordering sensitivity in 30 to 50% of CP phase angle. For DUNE, it's under construction, and it has exciting physics programs will decisively determine CP violation and mass ordering for neutrinos, and also can do other physics. And the technical design has been done, and the far detector site is under excavation. And we also have run very successfully the prototypes for the DUNE far detectors at CERN. And for the machine learning, NOVA actually already published physics results with these deep learning methods. And also many deep learning methods are developed for the particle identification and energy reconstruction, etc. And the aim is to develop a full AI or machine learning based reconstruction chain for both NOVA and DUNE. And as you can see from the last slides, machine learning can also enhance the parameter inference for NOVA for neutrino oscillation experiments. Okay, that's all I have. Thank you very much.
Thank you very much for that very interesting talk. Do we have any questions for you? So just either raise your hand in the chat or just speak up. All right, so while they're thinking, I have a question. So has the schedule that you gave for DUNE been delayed at all by the recent events, or are you still?
So the official statement is will still run the beam in late 2020s, but there's not such a previously we scheduled it at in 2016 and then delayed it a little bit to 2016, but now it's the statement is late 2020s. So
Okay.
not sure if the 17, 18, or 19. Yeah.
Okay. Well, that gives you a little bit of time anyway. Any more questions? I think that was one there, but it cut off whoever asked it. Okay. Okay, I wanted to ask you a technical Gaussian process question, which I'm going to do because no one else is asking. I would have asked you afterwards otherwise. So how many data points do you train on for your GP?
You mean the Gaussian process?
Yeah, how many do you need? Is it order of 100, or is it?
So actually, here's the thing. So it's a iteration process. So we first generate maybe 1% of the data points, and then use the Gaussian process to. Let me go to there.
Oh, so you use a full Bayesian optimization to do this?
So actually, yes. So
Ah.
actually, here is the process. So first we use a regular process to generate a small number of data points, and then use the Gaussian process to make an estimate, right? That's the first iteration. And then we go to the interval level we're interested in, close to the, for example, 90%, for example, and then we generate more data to make a better estimate, use this Bayesian process. So as long as you go this iteratively, so you can achieve 100% accuracy. So actually, it's not a really Bayesian process. We use Bayesian process to better choose the point in the parameter space and to generate new toy simulations. And then so therefore we can fast we can achieve the contours of interest very fast, much faster than Gaussian process than the traditional Feldman cousin, because traditional Feldman cousin just generate them without difference, right? Every point are treated evenly. And now we use this Bayesian process to go to the interesting contours or the interval values, say with just one or two iterations. So this is how we save time. And then theoretically, there's no bias or no difference as long as you generate sufficient points. But this number is still much smaller than the traditional Feldman-Cousin method. Yeah.
Thank you. That's really impressive.
I have
Hyber has a question.
Hey, yeah. First of all, I'd like to apologize. I actually came very late. I just realized today that the Colloquium, there's so many meetings. Okay. I just have like two questions. So one is that, you know, a couple of years ago, I heard that people wanted to do something with the ice cube experiment. They call it deep core or something like that. And, you know, you probably in some very focused region, you can build more detectors over there. Probably you can also, the measurement with ice cube can be sensitive to some fundamental properties of not dark matter, the neutrinos, right? So even like say pure mass hierarchy. Do you know all those efforts are still going on, or they just, because of DUNE, that it just cut off?
I think it's not cut off, but they as far as I know, they changed their plan. The very original plan is to have a better resolution, and right. So and then they place more PMTs, the photon sensors, use more region and have a better sensitivity to the muon neutrino. In this way, they can mirror the math hierarchy, just a similar way as super here. But then they realized or be forced to think that this setup won't be able to compete other experiments like NOVA, DUNE, and Juno in China, for example. And so I heard they changed their direction by placing more sensors in a larger region, and therefore they are good to measure the high energy neutrino. And the advantage of this is that they will have a better measurement to the tau neutrino, and by measuring tau neutrino, they can kind of measure the unitarity, right? If you measure both electron neutrino, muon neutrino, and tau neutrino, you can add them up to figure out the unitarity. And I think this is their current direction. But if they have already have the solid support from NSF, I'm not quite sure. But they are not killed yet, I believe.
Okay. A related question is that in Japan they are planning like a hyper-K, right? So could you talk about the general bigger picture in terms of neutrino physics in the next, let's say, 10 years or 20 years? And of course, on the US side, we have DUNE, and in Japan, they are hyper-K. And but maybe those goals are complementary, right? So yeah, could you comment on that?
Yeah, so I think with DUNE and hyper-K, CP violation and mass hierarchy will be so mass hierarchy will be determined by DUNE very shortly, and hyper-K, I would think they might have a better sensitivity or comparable sensitivity to CP violation. But in the next, I think not 10 years, next 20 years or so.
20 years.
Yeah. The mass hierarchy and CP violation will be sure, and plus the Juno experiment in China for mass hierarchy. So these two variables will be determined, and beyond that, I would think probably so the direction that the ice cube goes, like the unitarity test, beyond standard model, and also some measurement for the, let's say, dark matter and stereo neutrino with intensive beam. That probably the doable thing after the standard model oscillation is determined. That's and then also there's, I think the absolute neutrino mass is super interesting, and there's some developments using the using electrons to determine about measure the electron the electron momentum, but it's very hard. But if it can be determined, that would be very interesting for many reasons.
Yeah, I think for that maybe the cosmological problems have some very good sensitivity. Simi actually is an expert on this. So
I think from when I joined this field like 10 or 15 years ago, the number is like 1 EV, but now they now say sub 1 EV already. But but also there are other experiments can measure the absolute mass, but it's hard. But it's figured out, and as well as mass ordering, it's very super useful. One is for this Mariana particle determination. Right? If you have a normal mass hierarchy and the current experiment have nearly no hope, but if it's a inverted mass hierarchy, you have a very good chance to determine whether neutrino are there antiparticles in a short period of time. That's it's very interesting. And also I'm not expert, but you perhaps know if we know the absolute neutrino mass, how the grand unified theory can be developed, etc. Thank you.
All right, well, thank you very much again. Any more questions? Okay, well, thank you very much again for coming to talk to us. That was very interesting, and best of luck with these neutrino experiments.
Thank you very much for the invitation again.
Bye bye now.
So